It's 3 a.m. and one of your cache servers just died. You had 3 servers splitting the load evenly. Users were happy, response times were fast. But now, with one server gone, something terrible happens. Every single cached item is suddenly on the wrong server. Your cache hit rate drops to 0. Every request now slams directly into your database, and your entire system starts to buckle under the load. This is the nightmare of naive hashing in distributed systems. When the number of servers changes, almost everything has to be reshuffled. But what if there was a way to design your system so that when a server crashes, only a small fraction of your data needs to move? What if adding a new server was just as painless? That technique exists. It's called consistent hashing, and by the end of this video, you'll understand exactly how it works. Let's start with the approach that breaks, naive hashing. You take a key, run it through a hash function, and then compute the result modulo n, where n is the number of servers. Hash of key mod n gives you the server index. With 3 servers, each key maps neatly to server 0, 1, or 2. Let's say we have 8 keys. They spread across the 3 servers fairly evenly. Everything looks great. But now, remove one server. N goes from 3 to 2. Recompute every key. Hash of key mod 2 instead of mod 3. Watch what happens. Almost every key now maps to a different server. About 2/3 of your keys just moved. For a cache, that means 2/3 of your data is effectively gone. And if you add a server instead, going from 3 to 4, the same thing happens. Most keys reshuffle. This is why mod n hashing is a disaster for any system where the number of nodes changes. Here's the key insight. Instead of thinking in slots, think in a circle. Imagine a number line from 0 to 2 to the power of 32, but with the ends connected. 0 wraps around to meet the maximum value. This is the hash ring. Now take your servers and hash their names. Server S0 might hash to position 1 billion. S1 lands at 2.5 billion. S2 ends up at 3.8 billion. Each server becomes a point on this ring. Notice what's different. We're not dividing by the number of servers. We're not using modulo at all. We're just placing servers at fixed positions determined by their hash values. The ring doesn't change when servers come and go. The positions are absolute, not relative. This is the foundation of consistent hashing. The hash space is a fixed circle, and servers are simply points placed upon it. Now let's put data on this ring. Hash your data key the same way you hash the servers. The key lands at some position on the ring. To find which server is responsible, start at the key's position and walk clockwise around the ring until you hit a server. That first server you encounter is the one responsible for this key. Simple as that. Each server effectively owns the arc of the ring between itself and the previous server in the counterclockwise direction. These arcs partition the entire ring into regions, one per server. If a key lands in the teal region, server S0 handles it. If it lands in the lavender region, it goes to S1. The amber region belongs to S2. This is the lookup rule for consistent hashing. Hash the key, land on the ring, walk clockwise. It's deterministic, it's fast, and as we're about to see, it's remarkably stable when things change. Here's where consistent hashing shines. Let's add a 4th server. Server S3 hashes to a position on the ring, landing between 2 existing servers. It slots right in. Now look at what happens to the keys. Only the keys that were in the arc between S3 and its counterclockwise neighbor need to move. These keys used to belong to the next clockwise server, but now S3 is closer. They migrate to S3. Everything else stays exactly where it is. The other servers don't lose a single key they weren't supposed to. With naive mod and hashing, adding a 4th server would shuffle about 75% of your keys. With consistent hashing, only about 1/n of the keys move, where n is the new number of servers. That's the magic. On average, only k over n keys need to move, where k is the total number of keys. The impact is proportional and minimal. No thundering herd. No cache avalanche. Now let's go back to that 3 a.m. crash scenario. Server S1 goes down. In our hash ring, its point on the ring disappears. But what happens to S1's keys? They simply slide clockwise to the next server on the ring. S1's entire range of keys gets absorbed by its clockwise neighbor. No other keys are affected at all. Compare this to naive hashing, where losing one server out of 3 reshuffles about 2/3 of all keys. With consistent hashing, only 1/3 of the keys move, and they all go to a single known destination. This makes recovery predictable. You know exactly which keys need to be refetched or re-replicated. There's no system-wide disruption. And this works just as cleanly whether the server crashed unexpectedly or was deliberately removed for maintenance. The ring adapts gracefully in both directions, adding and removing servers with minimal data movement each time. But consistent hashing has a weakness, and it shows up when you have a small number of servers. With only 3 servers, their hash positions are essentially random. They might cluster on one side of the ring, leaving huge gaps elsewhere. Look at this ring. Server S0 ended up very close to S2. That means S0 owns a tiny sliver of the ring, while S1 owns a massive arc, maybe 60% of the entire hash space. In practice, this means S1 handles the majority of all requests. It's overloaded, while the other 2 servers sit mostly idle. This is the hotspot problem. Even worse, if the heavily loaded server crashes, all of its keys flood into the next server, which then becomes the new hotspot. You get a cascading failure. With a large number of servers, the distribution tends to even out naturally. But in most real deployments, you don't have hundreds of physical servers. You might have 5 or 10, so we need a fix. The fix is elegant: virtual nodes. Instead of placing each physical server at a single point on the ring, we create multiple replicas. For server S0, we hash S0-1, S0-2, S0-3, and so on. Each hash gives a different position on the ring. These are virtual nodes. Each one maps back to the same physical server, but they're scattered across the ring independently. With just 3 physical servers, but say 150 virtual nodes each, you now have 450 points spread around the ring. The arcs become much more uniform. Look at the load distribution. Before virtual nodes, one server might handle 60% of the traffic. After, each server handles close to 33%. The variance shrinks dramatically. Most production systems use between 100 and 200 virtual nodes per physical server. It's the standard practice in systems like Cassandra and DynamoDB. And just like that, the hotspot problem disappears. Consistent hashing isn't just an academic concept. It's running in production at massive scale right now. Amazon DynamoDB uses consistent hashing to partition data across storage nodes. When you write a key-value pair, consistent hashing determines which partition owns that key, and virtual nodes ensure even load distribution. Apache Cassandra takes it even further. Its entire architecture is built around a token ring, which is literally a consistent hash ring. Every node in the cluster owns a range of tokens, and data is distributed and replicated using this ring structure. Content delivery networks like Akamai use consistent hashing to route requests to edge servers. When a user requests a web page, the URL is hashed to determine which edge server should cache and serve that content. And distributed caches, like Memcached clusters, use consistent hashing to spread cached items across cache nodes. This way, adding or removing a cache server doesn't invalidate the entire cache, just a small fraction of it. Let's bring it all together. Naive hashing uses mod n, and when n changes, almost everything moves. It's simple but fragile. Consistent hashing fixes this with a hash ring. Both servers and keys are mapped onto a circle. To find a keys server, walk clockwise. When you add a node, only the keys in one arc need to migrate. When you remove a node, only that node's keys move to its neighbor. The rest of the system is undisturbed. Virtual nodes solve the load imbalance problem by giving each physical server many positions on the ring, ensuring even distribution. And this technique powers some of the biggest systems in the world, from DynamoDB to Cassandra to the CDNs that deliver your web pages. Consistent hashing is one of those ideas that's simple enough to explain in 10 minutes, but powerful enough to run the infrastructure behind the internet. Thanks for watching.